Hi, this is Audrey Munger, and this is my Lab 3 on the black hole. The main purpose of this lab is to manipulate two GlowScript starter codes to determine the mass of a black hole. We will also calculate the gravitational forces of the black hole. In part 2, we will determine the initial velocity needed for the spaceship to get close enough to observe the black hole without getting sucked into it. The main results of the lab are that the mass of the black hole is 7.33 times 10 to the 43 kilograms, and that the initial velocity of the spaceship is negative 7.01 times 10 to the 6 in the x direction, and 9.45 times 10 to the 6 in the y direction. The system is the spaceship, and the surroundings are the black hole and the planet. The two main physics principles covered in the lab are Newton's second law and gravitational force. The main equation for Newton's second law is F net equals dp over dt, and we can split that equation into F net equals dp over dt parallel plus dp over dt perpendicular. A derivation of these equations we will use in this lab is F net parallel equals dp over dt times p hat. The equation for gravitational force is the force of gravity is equal to the universal gravitational constant times the mass of both objects divided by the distance squared, all multiplied by r hat. In this lab, we'll use a derivation of this equation that solves for the mass of one of the objects. Looking at my Part 1 code on the left, you can see I entered in my Georgia Tech email address for randomization, and the code on the right shows more physics constants needed for the calculations. Here I'm showing more of my Part 1 coding. The coding on the left shows more physics principles like the momentum principle at line 165, and calculating for the net force parallel and net force perpendicular. In the code on the right, I solved for the mass of the black hole using a derivation of the gravitational force equation. From the coding in Part 1, I got my results as F net is equal to 3.31 times 10 to the 8th, and F net parallel is equal to 1.17 times 10 to the 8th. I also got F net perpendicular equal to 3.1 times 10 to the 8th, and the mass of the black hole is 7.33 times 10 to the 43rd. On the left, you can see some screenshots I took of the orbit while it was running. The coding in Part 2 is used to solve for the initial velocity of the spaceship. This required some trial and error to reach a point where the spaceship would not get sucked into the black hole. On the left side, you can see my black hole's mass that was calculated in Part 1, and on the right side you can see how the gravitational force is calculated between the black hole and the planet, and the spaceship and the planet. We use the code to solve for the net force on the spaceship by adding the force from the planet and the force from the black hole. The velocity update and position update formulas at the bottom are used to calculate the final velocity and final position. Then, using a while loop, we can find the spaceship's initial velocity. We found that the spaceship ended 2.9 times 10 to the 10 meters away from the event horizon, and the spaceship's initial velocity is negative 7.01 times 10 to the 6th in the x direction, and 9.45 times 10 to the 6th in the y direction. For the discussion portion of this lab, the what if question asks, what initial velocity is needed for the spaceship to enter into orbit? This would require more trial and error to find a specific velocity, but I know the magnitude would be greater in the y direction than what I calculated in Part 2 coding to allow for a more circular shape. For the what does it mean question, we know that the rate of change of momentum is equal to the applied force. In this lab, we use the equation F net equals dp divided by dt, so we can assume that F net is equal to this value.